Today we're going to see how easy it is to use TIBCO StreamBase in an ETSI NFV MANO compliant environment. And as part of the demo, we'll show how we can scale out and back in our virtual network function. So what we'll see during this video is the creation of our StreamBase VNF and then how it's deployed, executed, scaled and then terminated. Now there are a number of moving parts in this demonstration, so let's take a look at the logical architecture to get an understanding of what's going on. So this diagram is going to be recognized by anybody familiar with the Network Function Virtualization or NFV architecture. For the MANO or Management and Network Orchestration component of the architecture, we're going to use an open source project called Baton. Now Baton is a fully compliant ETSI NFV MANO. Now, Baton has a dependency on RabbitMQ for messaging and Zabbix for monitoring of compute resources, such as CPU utilization and memory usage. However, one of the benefits of using Baton is that the open source project includes a virtual network function manager, an element management system, or EMS, and it also comes with an auto-scaling engine. In addition, Baton provides multiple VIMs, or virtual infrastructure managers, for OpenStack, AWS and Docker. For this video, we're going to use the OpenStack VIM. And that leads us on nicely to the next key component, OpenStack. And OpenStack is providing the NFV Infrastructure, or NFVI. Now, OpenStack is another open source project, but has significant backing from major organizations and does appear to be becoming pervasive in the cloud computing domain in telco networks. Last but not least is the network service itself, which is going to be made up from TIBCO StreamBase VNFs. So out of all of the TIBCO products, why TIBCO StreamBase? If we think about the challenges of telecoms organisations today and the promise of 5G, we'll see not only a step change in volume, but also in the number of connected devices. But moreover, it's the wide range of use cases that will need to monetize that capability. And to underpin those business use cases, technical capabilities such as scale, agility and latency will be absolutely key. So StreamBase falls squarely into this category, with well-proven capabilities such as distributed GeoHA memory, temporal event correlation and aggregation, AI and machine learning closed-loop analytics, which allow the analytic algorithms to run in real time in the policy control function control path, for example. Some of this is complex stuff, not only the functional capability, but also needs to be agnostic of deployment environment. And to this end, StreamBase makes these complex capabilities easy to wield for a wide range of different users. So before we get started, let's lastly look at the physical environment that's deployed. So we have our MacBook Pro running StreamBase Studio, where the VNF is going to be developed. We have Zabbix and Baton deployed using Docker containers on their own virtual machines. Then we have OpenStack running on its own bare metal server deployed using Ansible. So OpenStack will be our infrastructure hosting our network services made up from our TIBCO StreamBase VNF. As part of the demo, we connect to an MQTT broker, and we'll see why this is later. In addition, we're using GitHub to store our VNF application, various element manager scripts, NFV descriptor files, which will be cloned during VNF installation and startup time. And all of the runtime servers are using Ubuntu 16.04 operating system. Okay, so let's just briefly run through what we'll see in terms of the demo. First of all, what we'll see is how the VNF is built using StreamBase Studio. Then we'll see at 2, the Baton MANO requesting compute resources from its NFVI OpenStack, followed by the MANO then deploying the network service and its VNFs. And there we'll see ETSI standard lifecycle events such as initialize, configure, start and so on. Then you'll see the network service VNFs being monitored by Zabbix, and then we'll see at 4 the auto-scaling of our StreamBase VNF. Okay, so let's take a look at what our StreamBase VNF application is actually going to do. So what we're looking at on the screen at the moment is the StreamBase Studio, and from here we can very rapidly build, test and deploy event stream applications. StreamBase applications are made up of very small streaming fragments, or microservices or microstreams. And once built and tested, we can combine these fragments together in different ways to form your virtual network function. And so we see here our StreamBase fragment, which is going to form the basis of our VNF application. These are very simple and quick to build by simply dragging over the palette items such as the operators and adapters or data constructors, dragging them over to the canvas, wiring them up and configuring. For the purposes of this video demonstration, we could have gone for something more telco specific such as policy control or online charging and so on. However, for the purposes of this video, it's more important to understand how StreamBase can be configured and deployed as a virtual network function. And so in this case, I've gone for a much simpler service that can be rapidly understood. So what this VNF is going to do is publish information onto a MQTT broker. So how does this work? So we have a metronome, and as that suggests, it sends out a trigger every configured period. And this trigger launches a bash script configured inside the external process adapter. The script that gets launched could do anything. In this particular case, we're going to capture things like the host name, CPU utilization and so forth. And this will make it much easier to see when we auto-scale which VNF instance is reporting what usage, etc. The output of the bash script then gets passed into the next downstream operator there, which you see called map, which takes the output of that bash script and transforms it in the correct form that can be published to an MQTT broker. So it will have things like the topic name, the payload itself, and the quality of service. So the output of the map operator feeds the MQTT client publishing adapter, and this will publish our stream's payload to a configured MQTT broker. Actually, while we're here, we can see there are other input streams feeding into my fragment. And this should give you some insight into the fact that the StreamBase fragment could consume, aggregate and correlate multiple data sources such as diameter or HTTP, HTTP2, etc. So although we're scratching the surface here, StreamBase really is a very powerful and agile streaming analytic processor to create virtual network functions. Now the ETSI specification for network function virtualization specifies a number of descriptor files, such as the network service descriptor and network function descriptor. And specifically in the network function descriptor, it allows the configuration of parameters to be passed into the VNF to be launched. So in our simple example, we might want to pass in or change parameters such as the metronome frequency, or the MQTT topic name, or the broker on which to publish. And so in this particular example, I'm going to be setting through my descriptor files the name of the broker that I want to publish to. So how might this work? Let's look at how we might configure the MQTT broker ID. If you take a look at the screen, you'll see there's a configuration parameter called MQTT connection. And in there I've specified a variable called MQTT_broker. And what that means is that the implementation that Baton has made, which adheres to the NFV MANO specifications, its element management system is able to take the parameters defined in the descriptor file and convert them to environment variables, which StreamBase can easily pick up using this configuration approach. So the next step is to use the StreamBase Studio to build and test a deployment archive. The ETSI NFV MANO specification allows its repositories to be local or external to the MANO. So what we're going to do is we're going to store our StreamBase VNF archive on GitHub, and then we'll see later on in the video how that is used in the VNF lifecycle. Okay, so we have mentioned NFV descriptors a few times, so let's take a look at what the descriptors look like for our application. Okay, so here's the GitHub repository that I'm using for the demo. Here we're storing the descriptor files, the application archive itself, and a number of scripts that form part of the installation and startup process for the VNF. So let's look at the descriptor files, and the first one we'll look at is what we call the Virtualized Infrastructure Manager, or VIM. The VIM configures the point of presence for the NFV infrastructure, and what this means is it's the point of presence for your infrastructure provider. In this case we're using OpenStack, but it could easily be AWS or Docker, for example. It allows connection to be made to the infrastructure, and then what happens is that the Virtual Infrastructure Manager gets all of the resources that are available on OpenStack. So things like images, hardware flavors, keys and so on. So in the VIM, you have to define things like the IP address, the authentication information to the selected infrastructure, and give it a unique name because you'll be referring to that later. It is possible to have multiple concurrent VIM configurations at the same time, so it would be possible, for example, to deploy your VNF into AWS and into OpenStack. Okay, so let's move on to the next descriptor, which is called the VNF descriptor, or VNFD. This is the main configuration for your VNF. So there's lots of configuration items here, but let's just focus on a few. For example, it will define which Vim instance you want to deploy on. So this was the importance of setting a unique name for your Vim, and you'll notice it's the one that we actually defined earlier. Moving down the descriptor, you can see the configuration section. And in this part of the descriptor file, we have the configuration of parameters. So this is where we will be defining the parameters that we want to pass into our VNF. And you'll remember that we had defined which MQTT broker that we want to use. In fact, I'm configuring a few other things like the metronome time and the topic name. And then via the element management system, the EMS, our StreamBase VNF will pick up these environment variables as we showed in the earlier part of this video. Moving just a bit further down the VNFD, we can see where the MANO's lifecycle events are defined. And these lifecycle events are ETSI specified events that must be supported. And so these are the events that will instantiate, configure, start, stop, etc. your VNF. There are several events, as you might imagine. We've only got a few defined here, but other ones, for example, might be upgrade or restart and scale out, for example. What's important though to note here is that the mapping of the event to a script file, and it's the script file that actually implements the functionality of the step. So for example, in the Baton MANO is mapping the ETSI event instantiate to a bash script called demo_install. And it's in this script where we do all of the necessary steps to instantiate our VNF. And similarly, the start event is mapping to demo_start, and it will do everything that's needed to start the VNF. And so this is how Baton's generic VNFM, that's Virtual Network Function Manager, is mapping the ETSI specifications or events to its implementation. And so again, these scripts are on this GitHub repository. We'll take a look at those shortly, but again, they could be defined in the MANO's own repository, or you can put it on an external repository. Further down the VNF descriptor is where we define the auto-scaling policies. So this is where we define the metrics on what is it we're going to measure to decide whether to scale out and how we'll scale back in again. So looking down this, you can see here that I'm specifying that we want to look at the average CPU user load. And I'm specifying here that a scale out event will occur when the average CPU load exceeds 70% for a minimum of 30 seconds. And the scale out count is 1, which means that it will scale out one instance at a time when those metrics are met. Scaling policies are pretty much the same, but except we're looking for less than 40%, which exists for 30 seconds, and then we'll scale in using the scale in policy. Another key configuration measurement here is what they call the cooldown periods, which is set to 120 seconds, which means that after I've taken an auto-scale decision, whether it be scale out or scale in, we have to wait a configurable, and I put 2 minutes here, for settlement time. So this allows the systems to settle before it starts making another scaling decision. Okay, so the last descriptor we'll take a look at is called the network service descriptor. So an actual network service, for example, might be a PCRF, an OCS, a network gateway of some sort, and it will most likely be built up from more than one VNF. VNFs tend to provide very specific functions, and we combine those functions together to make up a network service. So here in this network service descriptor is where we can define the virtual network functions that make up this network service. Now in our particular example, it's a one-to-one relationship, so we have one network service made up of one virtual network function, our StreamBase function. But you can see there we could list a number of VNFs to make this network service work. The other thing that you can define here in the network service descriptor is inter-VNF dependencies. So you can have different types of VNF. For example, you could have a client VNF, you could have a server VNF. There are other types. And so you might find that you have a dependency of one VNF on another. Now it's a little bit mute in our case because we only have one VNF. So what I have configured is our floating IP address that's allocated to us from OpenStack. So this can be a very granular implementation. We can define many StreamBase fragments to make up a single VNF, and we can define a network service at the ETSI specification level made up of one or many VNFs. So in the demo, what we'll do is we'll instantiate configure start using the ETSI defined events. The StreamBase VNF will start and we'll see it publishing to the broker every 3 seconds. And then what I'll do is I'll stress it for a period which is long enough to trigger the scale out, and then I will leave it alone. We'll wait for the cooldown period and then we'll see it scale back in. Okay, so now we're getting very close to the point where we're actually going to deploy our virtual network function as a network service. So what we've seen so far is us building the virtual network function, the VNF, using StreamBase, and how we've configured using NFV compliant descriptors to define its life cycle, parameters, and how it's going to be included into a network service. Now what we're going to do is deploy the network service onto an openstack infrastructure using OpenBaton's NFV compliant MANO. So first of all, let's log into OpenBaton. And here we see the OpenBaton summary dashboard, which really shows us a mixture of a catalogue of available descriptors and services and the actual running services. So we can see at the moment actually that we have no virtual network functions, no network services defined in the catalogue, and no network service record, which is the representation of a running instance of a network service. I have already defined a user key to save time in the demo, and this key is really to allow OpenBaton and OpenStack to communicate with each other, and also for us to be able to log into OpenStack instances. On the left hand side here it shows similar information, but from here we're able to drill down much further into the catalogue, definitions and instance information, and we'll see this shortly. So we can see here that there is nothing defined, nothing running, not even our vim or point of presence into OpenStack. The only thing that is defined and actually is running is the generic VNFM, the generic Virtual Network Function Manager, and this component is actually provided by OpenBaton and is started when the MANO Docker containers are brought up. So we've already seen a number of the descriptor files, and what this OpenBaton UI allows us to do is to actually create the descriptors via the UI. But as you may recall, there are lots and lots and lots of things to configure. So through the UI, this would probably take too long, so you'll be pleased to know that we're not going to use the UI to define these descriptors. In fact, what we will do is we will use the OpenBaton's API and command line interface to deploy the descriptors that we've already written. So here we have a bash shell, and I've already cloned the GitHub repository, and you'll see the various descriptors we already looked at. And I've included here a simple little script that sets up the command line environment, and it executes just at the bottom there the OpenBaton CLI command. So the first thing we need to do is instantiate a vim towards the OpenStack instance. Now the OpenStack instance is already up and running, and we'll take a look at that a little bit later. But here's the vim configuration that we saw earlier, with the names of the OpenStack credentials, security groups, and key definition. Now when I use the command line to create the vim, it will instantiate a point of presence for our OpenStack instance. And once established, the vim will fetch the available OpenStack images, hardware flavors, and so on. So here we go. After this command executes, we will have connected the OpenBaton NFV MANO to our OpenStack infrastructure. So once the command is executed, we get a textual response shown here with all the data retrieved from the OpenStack instance. Now it's a bit easier to see this through the OpenBaton UI, and so we can see here the available images, the hardware flavors that we can choose for our network service. So the next thing to do is deploy into the MANO catalog is the VNF descriptor. However, the VNF descriptor, like the StreamBase application itself, has no knowledge of the infrastructure it's going to be deployed on. At this point, it actually could be OpenStack, it could be AWS or something different. So what we need to define is some metadata which will link the descriptors to a target deployment infrastructure. If we look at the metadata file here we've got open on the screen, we can see that the Vim type in this case is OpenStack, which means that the Vim will validate that the target infrastructure is OpenStack before deploying the VNF. We also see the scripts link parameter, which specifies the location of the scripts that will be implementing the NFV lifecycle events. So this is important as the scripts may have different implementations depending on the target deployment infrastructure. The remainder of this metadata file specifies the image the VNF requires. The actual configuration allows us to check to see if this image already exists on the OpenStack instance, and if it doesn't, we have the option to download it from an image repository specified in that link parameter. For this demo though, we've already preloaded the image onto OpenStack just to save time, and we'll see how this was done a bit later. So the MANO allows us to bundle the metadata, which has knowledge of the deployment infrastructure, and the VNFD into a single tar file, and then using the CLI commands to create the VNFD. So just a quick reminder, the VNFD is where we have things like the parameter definitions, the NFV lifecycle mapping, the auto-scaling policies and so on. And so we can tar these two files together using a simple script into what's called a VNF package, and then using the Baton MANO command line deploy the VNF package into the MANO catalog. So we type in Baton VNF package create and the package name. And so now if we quickly switch to the MANO's graphical user interface, we can see now that we have a VNF descriptor in the catalog with all the parameters that we have configured in our descriptor files. So one of those parameters sets were the lifecycle events. So just while we're here, we can quickly take a look at the number of different types of MANO events that we could leverage to support the behavior of our network service. So here we're showing you a list of the possible events like scale in and scale out as it happens, which we will make use of shortly. So the next step is now to put the network service descriptor into the catalog. And just as a quick reminder, the network service descriptor, we can combine multiple VNFs and define inter VNF dependencies. So now I create the network service in the same way by entering Baton NSD create and then the name of the JSON file which contains the descriptor definitions. And again, rather than going through the textual output, if we switch over to the UI, we can now see that we've got a network service descriptor in our MANO catalog. If we look into this, we can see it makes reference to our VNF descriptor, which we loaded just before, and with all the event lifecycle mapping, auto-scaling parameters and so forth. So now we're actually at a position where we have a configured network service in our catalog ready to be deployed and started onto OpenStack. The service is made up of a single VNF which contains a single StreamBase fragment or microservice. Alright, so now we're at a point where we can launch our network service. But just before we do that, there's a few things we just need to look at and remind ourselves of. So here on the Baton dashboard, we can see there are 0 network service records instantiated, and a network service record is an instance of the network service. Also, we've spoken a few times about the VNF lifecycle events and the scripts that implement these. So when the Baton MANO requests the launch of the network service, the scripts are installed onto the default element management system either from the Baton local repository or from an external repository such as GitHub. As the generic VNFM, Virtual Network Function Manager, issues these lifecycle events, the EMS will execute the associated scripts. So let's take a quick look at what these scripts look like. Let's just quickly switch back to GitHub, and I'll open up the demo install script, which is mapped to the NFV instantiate event. In this script, we print out some environment variables, and these are recorded in the log files. And it's just here, very importantly, we're cloning the VNF application or StreamBase archive. We pick up the parameters passed in from our VNFD, and then we execute the StreamBase administration command called epadmin, and we execute the install node command, passing in the VNFD parameters and StreamBase archive name. Now all of these scripts are pretty much the same. If we look at the terminate script, you'll see that it's very similar. However, here we are executing the StreamBase administration commands to stop and then remove the service. The other thing we should do before running our network service is to look at openstack. If we just log into openstack, we can see that we have no running instances. We can also see that we have some preloaded images, one of which we're going to use. We also have a number of pre-configured floating IP addresses. This is really handy because we have defined a floating IP as a VNF dependency. Lastly, there are some pre-configured security groups which we're also going to need. So just for completeness, so that you can see how this all fits together, after our OpenStack environment has started, I did run a script that preloaded and pre-configured these OpenStack resources. So if we open the script, we can see where we're creating the security groups, the keys, floating point IPs, and downloading and installing into OpenStack the operating system images. Okay, so let's go start our network service. For this, I'm going to use the Baton graphical user interface for a change. So let's go find our network service descriptor and select the action that we want to do. In this case, it will be launch. The first thing to note is that we're using OpenStack point of presence that we already configured, and we need to select the compute resource component our OpenStack is going to use. This is called Nova, and Nova is the open source project that allows OpenStack to provision compute resources. Next, we select the public key we're going to use to communicate with the virtual server that's launched. And then we have the option to change our configured parameters that we've already defined. We're not going to change any of these, so nothing to do here. The next thing we do is press launch to start our network service. Using the Baton UI, we can now see that our network service record has been created. And drilling into the network service record, we can see that compute resources have already been allocated and reserved for our network service. Drilling in just a bit further into the VNF itself, we can see how its life cycle is progressing. The life cycle events shown on this tab show the ones that we've configured in the VNFD, and the lifecycle events history shows the progress through those events. At the moment, we can see that granted and allocated events have been completed, which means that the Vim, the Baton Vim, has interacted with OpenStack. OpenStack has granted permissions to the Vim to be able to create the virtual server, and OpenStack has allocated and reserved the hardware resources specified by the flavor in our configuration. Now, the startup of the StreamBase VNF is pretty fast. So if I press refresh on the browser, we'll see the instantiate, configure and start events have now successfully executed. And if we switch to the OpenStack instance view, we have an instance that's running our VNF. We can look at the OpenStack overview and see all the compute resources available and what's been configured or in use. And drilling into the instance for a moment, we can see the floating IP, the image that we requested, and the flavors resources. So in theory, our StreamBase virtual network function is working, but let's check. Just as a reminder, the StreamBase application runs a script on the virtual server, and that picks up some basic CPU memory usage metrics, and we publish this every 3 seconds to an MQTT broker, the delay, the topic and the broker being defined as VNFD configuration parameters. So let's check that it's running, and to do this I have a simple Python-based MQTT listener which will connect to the broker and listen on the VNF status topic. And when we run it, there you go, we can see the CPU and memory usage around about every 3 seconds. So this is successfully running our network service, which is made up of our StreamBase virtual network function. What's handy to remember here is the host name. This is because in the next step, when we do auto-scaling, we will be able to see the messages coming from different instances of the network service. So at the moment we have our network service up running our StreamBase virtual network function, and it's working just fine, publishing data to the MQTT broker. So to get auto-scaling to work, we first of all need a way of monitoring our network service. And Baton supports an open source project called Zabbix to monitor these services. So Zabbix is very similar to many other monitoring tools and requires a Zabbix agent to be deployed onto the monitored instance. This is undertaken by the VNFM, which in conjunction with deploying the element management system also deploys the Zabbix agent, which will then report the system metrics back to the Zabbix server. Baton has an auto-scaling engine project, which when configured will register itself with the Zabbix server and then look for metrics such as CPU usage from the StreamBase service. The auto-scaling engine will then continuously apply the auto-scaling rules we configured in the VNFD. As a reminder, this was a scale out of one instance when we have an average of 70% CPU utilization for more than 30 seconds, and then scale back in an instance when the CPU usage is less than 40% average, with a 120-second cooling period between each scaling decision. However, to achieve scaling, we need to stress our CPUs that are running our VNF. For sure, our simple publishing application is not going to do that. So we have a simple stress application to simulate load. And this stress application was cloned by the script that implements the instantiate event. Now to run this stress application, we need to log into the instance running our VNF. So I quickly just need to look back at the OpenStack instances to get the floating IP address. And with this I can now switch back to the terminal so that I can log on to the instance using the security keys we already defined. So now I'm actually logged into our instance that's running our StreamBase VNF. From here now I run the stress application with some parameters, which basically means to stress out this instance for about 90 seconds. And so if I can enter the command correctly, there we go, we should now see the CPU utilization ramp up. So now let's switch back to Zabbix, and this is monitoring many metrics including CPU usage, and it's calculating the average usage over time. If we just wait a moment, and there it goes, the average is now about 65%. Let's just wait a bit longer, and there we now have the average is around 85%. And now we need to sustain this for 30 seconds or more, and it will trigger the autoscaler. So let's just wait a bit longer, and we'll quickly flip back to OpenStack, and we see that we still have one instance. If I keep refreshing the page, we should see in a moment the scale out. And there we go, the new VNF instance has scaled out with its own host name and floating IP address. So what's happening now is that the Baton NFV MANO is processing the scale out requests. And this will mean the StreamBase VNF is going through the same steps as before. It's gone through allocate and grant already, and now it's going through the instantiate, configure and start events. So now if I switch back to our little Python listener, we should start to see two VNF instances publishing data with their own host names and instance CPU and memory usage. However, what's interesting here is the 90-second stress period must have ended as the CPU usage is quite low. And this means that we've already entered into the 120-second cooling period. Let's quickly switch back to Zabbix and have a look at the utilization graph. And there we see it. We see the CPU growth resulting from the 90-second stress test, and then the CPU dropping off back to normal. So now after the cooling down period, we should see the StreamBase VNF service instances in OpenStack drop back to 1. So let's now flip back to OpenStack, and at the moment we still have two instances running. If we wait just a moment and I keep refreshing, and yep, there it goes back down to one VNF instance again. Just as a matter of interest, the Baton selects which instance to terminate randomly. So now let's take a look back into the Baton MANO and see exactly what's happened. If we go to the network service record, which represents the instance of our network service, and look at the VNF lifecycle history, we can see the entire lifecycle from resource allocation to the instantiation, configure, and the starting, and now we see the VNF scale out and the scale back in again. If we switch back over to the MQTT listener once more, we'll now just see one host name publishing data onto the broker. So the very last thing to do is actually terminate our virtual network function. In fact, what we're really going to do is terminate the network service. So this is easily done. We will switch to the Open Baton dashboard. We will then select the network service record and we simply select the delete option. What this is actually doing is deleting the network service record. It is not deleting all of the configurations. If I switch back to OpenStack and I refresh the browser, we see there straight away that the instance has disappeared. So that is the total instance shut down. Now it would have gone through a terminate cycle, so if there was any cleanups to do, the same mechanism would apply. The terminate event would trigger the terminate script. If we now switch back to the Open Baton dashboard, we can see that the network service record has gone. But the configuration files are still there, so if we wanted to restart the network service, we simply go through the launch process once again. And with that, it brings us to the end of the demonstration. So I hope it's been informative, and the key objective really was to show how a StreamBase fragment can be easily deployed as a virtual network function inside an NFV ETSI compliant environment. So it only leaves me to say thank you for watching and listening.